Okay, so this is joint work with Chen Avin and Zvi Lotker from Ben-Gurion University and David Peleg from Weizmann Institute. And the first thing I want to talk about is power loss. This is a very famous phenomenon that you can find in large-scale networks. So what is this power law? Well, first, before we define what it is, I'm just going to give you a bit of intuition. So we see this phenomenon in a lot of networks, large-scale networks, and also in some things that are not networks. These are a few examples. The second bullet is just network settings, and the third one is not. And to define power law, it's actually very simple. What we do is we take a network and we look at the degrees of that network, and then we build a function where we have the x-axis is just the degree, and the y-axis is just what's the percentage of nodes with that degree. Okay, so we expect this slope to go down. And a power law is basically if this slope is proportional to d to the some minus exponent, then we say that it's a power law. We have power law in the network. The degree distribution goes down as inverse polynomially in d. Okay, so this is the definition. It's very simple. And we see that in so many networks. Really, any large-scale network that you can think of has this power law. And because of that, in the literature, we have attempts to model a network in a way that it produces a power law. So how do we model a network so that we get a power law? This is just a reminder of what a power law is. And the first attempt, if you want to think of a model for a network, might be Erdős-Rényi, the GNP. It's very famous. The good news is that if you don't know what this model is or you don't remember what it is, it doesn't matter. Because the bad news is that although we know a lot of about this model, it doesn't really produce a power law. Okay, the degrees there go down exponentially usually. So we need to think of a different model to get a power law network. Okay, so this was all kind of introduction, and now I want to talk about the preferential attachment model, which is a model that was built in order to explain power laws in networks, basically. And I can just say a few words that it was originally proposed by Price and Barabashi to explain power laws. And I'll show the model in details later. But it has many variants. You can think of this model for directed networks, for undirected networks, full power law, all sorts of other things that we're not going to go into it. Now I'll just show you today a very simple preferential attachment model from 2006. The reason why I'm showing you this instead of the other many variations that we have is because this is the simplest model that kind of gives you a really, really, really good modeling of real life networks. Okay, so I'm going to show you right now a very, very simple model. And if this is everything that you take from this lecture, that's excellent. Okay, because that's basically very simple and it's very good to know, even if you know nothing about large scale networks. Okay, so I'm going to show you a model. How to build a network, basically. And we start from an initial graph, G0, pretty small. And every step, we're just going to add either edges or nodes, okay? Doesn't get simpler than that. So with probability P, we'll add a node. And with probability 1 minus P, we'll add an edge. How exactly do we add this node and edge? So in case that we go with the node event, with probability P, we add a node V. And we connect it to the network, okay, to some node U in the network that already exists in the network. And in the edge event, with probability 1 minus P, we just add an edge between two existing nodes, okay? So the only thing I haven't told you is how do we choose these existing nodes? So we choose the existing nodes with probability that's proportional to the degree, okay? So if I have twice as high degree as a different node in the network, then I have twice the probability of attracting more degrees even, basically. So this concept is also known as the rich get richer. So if you have a lot of degrees, then you're even more likely to get more degrees. If you have a lot of followers on Facebook, then you're even more likely to gain more followers on Facebook. And if you have a lot of money, maybe if you think of degrees money, so you can get richer easily. Okay, so this is the model. This is the whole model. It's a very, very simple model, and it's got great properties. The first thing is I'm going to show you is just before I talk about the properties is just a short demonstration So if we start with an initial graph of one node and one self loop, then we add nodes and we add edges, and sometimes we add an edge, sometimes we add a node, and we build this graph, and then we get, let's say, this particular graph. Okay, so this is just a demonstration to see how it works. And we said, well, this model was built to explain power laws. So the first result from 2006 is that this model does produce a network with a power law. And again, I remind you that the power law basically means that the percentage of nodes with degree D is inverse polynomial in D. Okay? And the second bullet is just to remind you what the model is. Basically, in one line, this is the model. Probability P, we add a new node, and probability 1 minus P, we add a new edge. And we just give a short notation. MDT will just be the number of nodes of degree D at time t, okay, because the network evolves with time. Okay, so the first result is basically that we have a power law. Okay, so if you look at the fraction of nodes with degree D, you look at the number of nodes with degree D divided by the total number of nodes in the network, and you put expectation on it. That's why I wrote expected power law. Then if you take this fraction ratio and you look over time, you take t to infinity, the time over to infinity, then you get some sort of function, which is a function of d. And you can show that in this model, the function is proportional to d to the minus from, the exponent there. Okay, so this is the result. Okay, so you see that you do get a power law, and the exponent beta of the power law is this thing, 4 minus p over 2 minus p. And because p is between 0 and 1, that's how probabilities work, then the exponent is between 2 and 3. So with this model, you can model any power law with an exponent between 2 and 3, which is excellent because in the second slide, I mentioned that the exponent is usually between 1.5 and 4 if you look at real life networks. So 2 and 3 is great. So this is a very simple model with a very powerful result. Here? This is great. Can you hear me now? Okay, great, sorry. And that was just for the expectation, and we also have a result, they have a result from 2006 that the number of nodes with degree D is also concentrated. So with high probability, you get that that function f that I didn't mention what it is, times p times t plus some error term. Okay, so we have these results from 2006, and they haven't been improved since. And I'm just going to mention a few problems, a few maybe things that you can improve in these results, okay, why these results are a bit suboptimal. So if you look at the first result, it only tells you what the expectation of MDT is, maybe, but it only talks about the limit, really. In the proof, they can't really bound the expectation, but they can prove that the limit tends to something. So it only works in the limit. If you want to know what the expected number of nodes is you just don't have good bounds on it, or any bounds. And it only works for fixed D. So it only works for fixed degree. So if you ask yourself, how many nodes of degree, let's say, square root t are there in the network? At time t, how many nodes of degree square root t? Then this will not tell you what it is. Okay, you can use the result. You can only use it for fixed d. So d equals 3, 4, 5. Okay, and the second result is something very interesting. If you look, there's an estimation, and there's an error term, that big O. And the error term seems to increase in D, which is very weird because we expect the number of nodes of degree D to go down with D. Okay, that's the power law, right? As we look at higher and higher degrees, we have less and less nodes of that degree. So it's a bit funny that the error term actually increases in D. So maybe we can improve that as well. So these are the results. And what we did is, so we take the first result, the expected power law. This is what they proved. And we were able to improve it, actually. If you look, this is the result, our result underneath. The expected number of nodes of degree D, we showed that it's fd times p times t plus a very small error term, okay? So this error term is not a function of t. It's just a function of the degree. And it's very small, right? It's less than constant even. So as you can see, obviously our result is stronger because the number of nodes of at time t is p time t. So you can, from our result, derive the original one. But it's much stronger than that. If we just look at our result for a bit, we can see that in order to get that the estimate is better than the error, it basically means that we can use this result to estimate the number of nodes at degree d for any degree that is O of t to the 1 minus p over 2. So if you ask yourself how many nodes of degree square root t there are in the network, so we can answer that, okay, using our result, which you didn't know before. Before you can only work it for constant d, and now you have something stronger. But it's actually stronger that if you look at, maybe if you don't want to just know the number of nodes of degree d, you kind of want to look at what people like to call the rich club of the network. It's just the people with a lot of degrees. If you look at the people in Twitter all the celebrities that have a lot of followers, and you ask yourself, how many celebrities do you have that have a lot of degree? Okay, so it's the rich club. You look only at the higher degrees. And the higher degrees, if you look at it, then we can also estimate that using our result. I didn't really show how, but you just sum it up. And you can estimate it for d that's almost as large as the first one. So for the highest degrees, if you look at their sum, then you can also estimate that. Okay, so we know how many. If you look at the rich club of maybe in the world, you look at all the people with the highest net worth, then you know how many there are using this result. Okay, so that was the first one. In the second result, we said this is the original result of the concentration. They proved that the number of nodes of degree d is something plus an error term. And we were able to improve that. We basically, not only did we improve the error term to square root of t, we were also able to prove something a bit more general. So if you take any subset of the degrees, that A is the subset of the degrees, you can think of like all even degrees. Or you can just choose, if you want to see that our result is strongest, you can just choose A that's of size 1. Okay, so you look only at one particular degree. Let's say d equals square root of t. So you see, we showed that it's even more concentrated than it was before. So it's the expectation, which we know how to estimate very well from the previous result, plus minus order of square root of t. So we already improved that. But so as we said, we can derive from our results that MDT is the expectation of MDT plus minus order of square root of t. But again, we can even look at all the high degrees together. Okay, all the people with the high degrees, and this sum is also concentrated with the error term square root of t, and that's just by choosing A only to be the high degrees. And you can also use it, by the way, to answer if you just take A to be all the even numbers. So you know how many, you can answer the question how many even degree vertices there are. So this is also something you can answer. And the question is, how tight is this result? And apparently this result is pretty tight, because if you just take A to be all the natural numbers, okay, so you look at all the nodes in the graph of whatever degree you want. So that's VT, the number of degrees in the graph. And by our result is basically the expectation of VT plus minus square root of T. And that is tight. We know that is tight. Okay, that's the best approximation we can give, unless P is equal to 0 or P equals 1. So this is so in that sense, this result is pretty tight. Okay, so that was the improvement of those results. I'm just going to use maybe one more minute to talk about a different result that we have in the paper. And that is, if we just look at this model, the model that I presented before, I just wanted to remind you that we get a parallel with the exponent between 2 and 3. So the question is, can we do a bit better? Can we maybe get, instead of between 2 and 3, maybe a wider range? Okay, we want to model more types of networks. And so that's one thing that we would want to do. And the other thing that we would want to do is maybe this probability P and 1 minus P, these probabilities don't necessarily stay constant with time, okay? At first, maybe with Facebook, you had a lot of people coming in, and then like everyone was on Facebook already, so you just had new friendships forming. So maybe P goes down with time. Okay, so we have another result that shows that if you choose instead of P and 1 minus P, you choose the probabilities that change, that vary with time, then you can actually get a larger range. Instead of a power law with exponent between 2 and 3, you can even stretch it all the way to exponent between 1 and 3. So if we just let that probability change a bit, then we can get a much larger scale of networks. I mean, more types of networks that we can model. And the last thing is that if we want, we can even stretch it from to a wider range, okay? And what we do is, if we have still the node events with probability P, and now the edge events, we add an edge with probability R, and now we add a different kind of event, we can add a component, okay? We add, let's say, 2 nodes that are connected between themselves, okay? 2 people joined Facebook and they friended each other. So if we have these 3 types of events instead of just the first 2, then we can actually get a power law, a network with a power law with any exponent between 1 and infinity. So give me any exponent that you want, and I have a model for you that can generate a network with a power law with that exponent, okay? So that's why we call it a full spectrum power law. And just to summarize what we did here is first I showed you what a power law is. This is just the definition of power law. And then I showed you the preferential attachment model, one of its variation, probably the most basic variation that kind of captures most networks out there. And then I showed you that we improved the long-standing result. And when I say long-standing, this is from 2006. So for 11 years, there hasn't been a progress in those results, and we improved that. We were able to bound degrees in the graph much tighter. And the last thing that I showed you is maybe a generalized model, a way to generalize the preferential attachment model and really produce any power law that you would want. Okay. Okay, thank you. That's it.